Okay, so the many worlds interpretation says that if I make a measurement here, yes, the particle is definitely localized to here in my world, but somebody else could measure it here and it's simultaneously localized here in their world. I think that's wrong because when we make a measurement of the particle at both slits at the same time, it can't be located at both places. It always chooses one place. Now, if we try to do it simultaneously, yes, that choice is probabilistic. There's a 50% chance it is playing dice. And so that's still weird and still goes against classical physics, but we don't measure multiple universes. Now, you could say, well, you're in the same universe, so that's why. But what defines what makes a different universe? I mean, if we're in a different point in space, even if we're at the same point in time, two users should be able to distinguish between their locality and their place in the universe. So I do think that many worlds is incorrect because if there were splitting of universes when we make a measurement, then different users who have different locations, even if they're at the same point in time, should have a different universe because the wave function splitting happens in this, continuous way. And so what defines what makes a different universe? Well, it should be a different location in space and time because that's how universes are divided up in terms of space and time localities. So since we never measure the particle to be at both places simultaneously, even if we had two different users, each with their own detector, we're not getting positive measurements. There's only one detection no matter what. So I think that's the area that many worlds is wrong. I think that many worlds is correct in that the wave function doesn't collapse. There's a continuity there where the wave function keeps going. It just changes. Okay, so here's my argument about quantum superposition being real and that measurement is a special thing. When this particle goes through, if we don't measure it, it behaves as if it goes through both slits. The Schrodinger equation says it's in a quantum superposition of a state going through this slit and a state going through this slit. But if we make a measurement, it's definitely here. But if we make a measurement here, it's definitely here. What this shows is that the measurement localizes it at the place where we're measuring it. If it didn't, when it's in a quantum superposition, if we measured it here, it might still be detected here. But that's never the case. So that is my argument that measurement actually does affect the wave function. Why do I think the wave function is real? Why do I think that objects actually have a distribution in space like a wave? And what's my argument for it? Okay, here goes. All these pioneers debated this, but there's something that they don't talk about a lot with the double slit experiment. When they make a measurement and actually measure the position of the particle and it quote unquote collapses the wave function, before they did that measurement, the particle could be said to be in a state where it's going through this slit and the other slit simultaneously. But as soon as they make a measurement, it's definitely in that state. What I say is that shows that doing a measurement directly affects the position of the particle. And so doing a measurement has an actual effect on the Schrodinger equation. And I actually have a mathematical equation to show this, which I'm working on right now.